And now I'd like to introduce the main event, our guest, Jeremy Spencer. Jeremy is a registered builder, thermal assessor and director at design and build company Positive Footprints. Jeremy is also a founding member of Builders Declare, an organisation started by builders for builders to help move the building industry to a low carbon future. Jeremy is also a member of the Design Matters Board and the Sustainability Hub, as well as being on the NatHERS, which is the Nationwide House Energy Ratings Scheme, stakeholder consultative group. Positive Footprints has won multiple awards for sustainability and works to show that energy-efficient, sustainable design and high-performance construction is a cost-effective option and can be a mainstream reality. Join me in welcoming Jeremy.
Start off with a bit of good news. The carbon intensity of the electrical grid is going down over time. We're now at about 8 tonnes. The average house in Victoria releases 8 tonnes of carbon dioxide per year. So still a lot, but heading in the right direction. Now, got a bit to go through today to answer this, but really what I want to talk about is a positive message that I want to bring today, and I want to let you know where the building industry is at and where it might be going in the future, as well as giving, if you're interested in building a home or a major renovation, give you an overview of what are the steps that you need to think about to achieve a net zero outcome today, which you can. Before I get into it though, I guess some bona fides. This is one of the homes that we currently build. Most of the homes that we build these days are what they call net zero carbon, in that they're producing more power over the year than they use. The first house that we had was back in 2013, where the owner sent us his bills and said that's what's happening at his place, and since then it's just become easier. This is one of our new Carbon Zero series. The difference is with this one, not only does it produce as much power as it uses, it produces a bit more to be able to charge an electric car and sets up for that. We also calculate the embodied carbon in the materials that the house is made of, and then put on a little bit extra so it can feed green power back into the grid and over time pay back its carbon debt, if you like. It takes about 20 years, but after that it's all completely carbon neutral. We call it true zero carbon. Now, I'm not showing this just as an advertisement, but also maybe to show you where the building industry could go and what we have the technology and the know-how to actually achieve these days. All right, let's get into it. How do we get to net zero? So here I'm talking about net zero operational energy use. So you don't need to be like this little scared guy, worried guy. That's sort of like the building industry at the moment. We're moving to 7 stars. So for those who don't know, at the moment, a new house, you have to get to 6 stars. That's the sort of the thermal score that you need to get higher than 6 stars. It's moving to 7 stars. We're also going to something called whole of home. Whole of home is where it also includes appliances, the fixed appliances in the house, to give more like a running cost for the whole house. It's a little bit more like the sticker that you get on a car when you buy a new car. You can see how much it's going to cost you to run. That's sort of where we're heading with whole of home. Net zero is actually going that little bit further than where the code is going, but I'm going to show you how to get there. And I guess the good news is you don't need to forge a new path here. You're not going boldly where no one has gone before to get to net zero. At this stage, thousands of homes across Australia have got to that net zero mark. And it's simply now a matter of just following what is, in fact, a well-trodden path to net zero. And if that looks like a little bit too much effort for you, you might like this better. Join the Congo line to net zero. And I think now that we've got this 7-star whole of home tool coming into the code, this will actually facilitate a Congo line tsunami of new homes coming online that have achieved producing as much power as they use over a year. Just to, I guess, highlight that point, at Design Matters National, the peak body for building designers and thermal performance assessors, where I sit on the board there as one of the hats that I wear, we started this competition last year, the True Zero Carbon competition, to produce homes that offset all their embodied carbon by 2050, when we're all supposed to be net zero. We teamed up designers and thermal performance assessors to get them used to working together, and actually getting to net zero operational energy. That was a low bar. They all blitzed that. In fact, most of them got to the true zero outcome as well. So we do have designers and thermal performance assessors that are starting to learn how to achieve all this. Now, before I go through the steps of this conga line dance, it's useful to outlay what the problem is, what the issue is. What you're looking at there is a pie graph of the average Australian home. So if you've got all the homes around Australia, new and old, and you average them together, that would be how the energy gets used inside the home. Most of it goes to space conditioning, as you can see there. Water heating is also big. Lighting and cooking are smaller. Appliances is a rather big pie as well. In fact, in Victoria and Ballarat, because we're cold, we get a little bit colder than a lot of the other states and use more heating. If it was a Victorian pie, our wedge would be past the halfway mark on the space conditioning. What that means is that the star rating system and heating and cooling appliance efficiency, you get a little bit more bang for your buck as far as what they save you when you install them in Victoria. Now, we talked about the average home in Victoria having 8 tonnes of carbon dioxide. In Australia, a lot of the other states are less carbon intensive than we are. The average for Australia is 6 tonnes of carbon dioxide. And as a fun fact for you, and just to give you an idea of what a tonne of carbon dioxide is like, yes, the average new home in Australia, 230 square metres, some of the biggest housing in the world. 2.7 ceiling heights typically. Now, if you took all the air out of one of those new homes and you replaced it with carbon dioxide, that house would then hold a tonne of carbon dioxide. So 6 tonnes of carbon dioxide is like 6 house-sized balloons sort of tethered to each home, and as you walk along the suburbs, one is sort of popping off here, popping off there. Every year for the life of the house. And a house can quite easily last 50 years. So somewhere around 300 to 400 tonnes of carbon dioxide could be produced by a house if nothing changed over that time. So an absolute mind-boggling weight in a gas. In fact, that's heavier than the weight of the average home itself. So a huge amount of waste comes up our homes because we're very profligate with our energy use in our homes. The good news, of course, is that we can get rid of that whole pie today. We have the know-how, we have the technology, and the price points are right. So that's what we're going to be doing. One of the know-how that we've got, before I get on to the actual steps of how to do it, one of the know-how that we've got is this NatHERS whole of home system that's coming out. And this is a schematic of it, just to give you an overview of what's coming into the code. This will come into the code in Victoria from October. This applies for all new homes and major renovations. So you can see it includes the thermal performance star rating. That's just on the shell of the house, how well the house sort of naturally heats and cools itself. But then it also starts to include the appliances, the space conditioning, the hot water, the lighting, cooking. Actually, I've got some slides to go through this. The star rating and the space conditioning, the efficiency of the house from its thermal performance and the efficiency of the heating and cooling plant that you put in it, that affects the space conditioning wedge of that pie we were just looking at. The efficiency of the hot water affects how much energy you use for the hot water wedge. Lighting, for the lighting, what you choose for cooking affects your cooking energy. Plug-in appliances in the tool itself, and this is actually moderated by 4 different software tools that assessors can use. They all share the same calculation engine that was developed by CSIRO. In the tools themselves, plug-in appliances gets inputted, but you don't get to fiddle with it. It's just an average amount of energy depending on the size of the house. It depends on how much appliance energy you put in there. But it's put in so you get an overview of how the house is likely to perform. Beyond the pie graph here, the tool also puts in, if you have a pool or a spa, it puts in the pump. It doesn't yet put in the heating of a pool, if you have pool heating, which obviously uses a lot of energy. And it doesn't yet put in car charging, though the trajectory for low energy homes talks about adding more modules, so that might be coming down the track. And lastly, it gives credit if you create your own power on site, depending on how much you create. And then the way the tool works, it simulates living in the home for a year. It does the thermal performance simulation, which I'll talk about a bit more later, but also having people in the house, having showers, turning lights on and off and that sort of thing, to work out how much energy the house uses. And then the house has to get to this 60 out of 100. So they've got a benchmark house, and you have to be more efficient than the benchmark house. And the benchmark house, the benchmark house is actually 50 on this scale. 60 is more efficient than the benchmark house. But importantly, I want to show you this. And this is really something that has not been brought out in the discussion of moving to 7 stars. On this code, you look along and there's 3 little words. It says net zero homes. So this is the first time that in the code we actually have a tool that we can use to design net zero homes, which is actually a really big step that no one is talking about. All right, let's get into these steps. So you want to design a new home, and also works for a major renovation. Now, I understand, obviously, if you're buying off the plan or you're buying a project home, you don't necessarily get involved in this. But if you're a designer doing those designs, you will be involved in this at some stage. Someone has thought about the design and has to get a rating done on it. All right, so we're now wanting to get to, if we want to get to a net zero outcome, there are 3 moves in this step, if you like, 3 moves. The first one is to get a good star rating. Now you have to get 7. 7 is now the minimum. You can think of 7 like 7 out of 10. It's sort of a B on a test. The old 6 out of 6 stars was like a C on a test. And these are professionals that we're talking about, professional designers. You'd expect if they do it day in and day out that a B, they can achieve a B, and it's not particularly hard once you know what you're doing. To get a B on the test, you simply need to design, and when you're doing your design, just put it through the prism of passive solar design. And this is just an age-old idea, and a very logical idea, of using the resources of the local climate to, in the first instance, try and maintain a comfortable temperature in your home. We're in a coldish climate here in Ballarat. Part of the year it's very cold. Well, it's as logical as, well, we just want to do a design that will allow the sunlight to come in, some good insulation, maybe a little bit of thermal mass just to hold that heat inside the house when the sun goes down. Simple things like that. In summer it gets hot here, so we want to have eaves that can shade out the summer sun but let in the winter sun. It's just very basic things. If you're in an area you get too hot, or in summer it gets too hot, well, you might want to design your layout for wherever the cooling breezes come from in summer. So in Ballarat, you've probably got some valley breezes that tend to come from a certain direction in the evenings of summer, and you just design the layout just to facilitate that for a little bit of free cooling. And if you're in an area where you've got a large diurnal temperature range, putting a bit of mass in the house or a slab on ground that locks to the stability of the earth means that you'll have a nice stable temperature inside the house. So these are just basic principles that are easy to learn. I won't be going over the rules. There are some rules of passive solar design. They're pretty simple, but I will bring your attention to this thing, net zero homes. I've recently done some work with Design Matters National and the South Australian Government, teamed up to create this webpage, Net Zero Homes, and we've got 5 modules on there, all on how to produce net zero homes. The first module is all about how to ACE 7 stars using passive solar design principles. So that should be coming out next month. Look out for it. It's free for the first 12 months. If you can't wait, with my other hat as Builders Declare, I did a talk last year on acing 7 stars. If you go about 20 minutes into that YouTube clip, if you search for Builders Declare acing 7 stars, it'll come up. You'll see the rules for passive solar design. And that's pretty much all you need to know to get a design to 7 stars when someone goes to rate it. Now, if you want to go to 8 stars, 8.5, 9 stars, 10 stars, if you want the high star outcome, there's one secret that you need to know. But if I tell you, you have to promise one thing. You have to promise to tell everybody. All right, so here's the secret. do 2 ratings. Do 2 ratings. It's pretty easy. One of my bugbears has always been that the thermal performance assessment was done as a compliance mechanism at the end of the whole design process. So the very last thing before you get your building permit, you'll get a thermal performance assessment done. Now, I used to do thousands of thermal performance assessments, literally, when I was getting positive footprints going. All the thermal performance assessor can do at that stage, they can't muck around with the design because you've already done town planning, you've already done working drawings, you've already done engineering. It might have been 2 years of hard work's been put into this design. All you can do is increase the insulation levels until it won't fit into the cavities anymore. And then if that doesn't get it to the minimum 6 stars, then you start going around the house double glazing windows until you get to 6 stars, then you stamp and you hand it back. So it's a recipe for minimum compliance. It's actually a recipe that may not work for 7 stars because it's a little bit of a harder bar. Sometimes on poor designs, getting to double glazing windows won't get you to 7 stars. Where I suggest you do this second rating is at design concept stage. So once a designer has done a design that you like, and you've mucked around it, we've got it how you like, that's when you do it, while the design is still quite fluid. Because the way the software works, you input all the data off the plans, all the dimensions, the areas, the volumes, what the materials are, what it's made out of, what the footing system is like, overshadowing objects, the size of the eaves, the performance of the windows, how big they are, what direction they're facing. You put in everything. The software then calls up the last 30 years of climate data in that area and then runs a simulation, doing a calculation every half an hour for every day for a whole year to work out what temperatures, if there was no heating and cooling, what temperatures would be in those rooms. And then if it's not already comfortable, how much extra energy would need to be put in those rooms to maintain a comfort level. And the great thing from that, from a design point of view, is a thermal performance assessor can straight away see, hey, this room's doing really well, this room's not doing well, what's happening in this room that's not happening in that room? And then they can start to play with variables. They can, maybe it's getting too cold, maybe we should pull back the eave a bit, get some more sun in here. Maybe we should, that window's in shade, maybe we should lift it up a little bit so it's in the sun there. Or maybe the room's getting too hot, maybe we should add a little bit of thermal mass to just slow the heat gain in that space. Or let's try triple glazing, see what it does. And then we can work out whether it's worth it. So if you do this at design concept stage, that's just a graph. So I'll skip through some of these if it doesn't quite flow. If you do that at design concept stage, an assessor can do what's called an optimisation report. And they can say, this is how the house is performing. These are things that you could do to increase the rating. And this is actually one of ours. We're a design and construction company, so we can go the next step and put costs next to those, so you can make some quantifiable decisions, not just it sounds like a good idea to do double glazing, but I don't really know, So anyway, this way I find we always do this, and even though my partner, the designer, my wife, Chi Lu, even though she knows passive solar design like the back of her hand, I can usually find about a half a star extra in this doing this. And if I'm doing a rating for someone who doesn't know anything about passive solar design, usually at least 1 to 1.5 stars from doing the rating at this stage. And now with whole of home, there's more that an assessor can give you. In fact, I would maybe stop calling them assessors and maybe start calling them consultants, because that is really what they are. Because now the tool, they'll be putting in appliances in the tool, they can give suggestions about which appliances are more efficient than other appliances, or trial ones that you want to use and see how that performs. They can also answer this really important question, and you should always ask this question if you're getting a design done. What size PV system would I need to put on the roof if I want to be net zero? Right? A really powerful question to be asking. Also, in brackets there, I've been talking with some of the software suppliers, and actually in the CSIRO calculation engine, there is the ability to find peak heating and cooling loads for certain zones, which is what you use to size up mechanical heating and cooling. So some of the software may very well be bringing that out as a feature, and you might be able to size up the capacity of your heating and cooling at that stage as well. Useful stuff at design concept. If you do want to get a thermal performance assessor on board, where do you find them? Well, you go to Design Matters, the member directory, the assessor lookup, and importantly, what you want to look for is whether they've done the whole of home certification. And in the next few months, assessors will be going through that process. Yeah, easily done. All right, so assuming you've done a good design, here's my pie, there's my space conditioning wedge. How much of that wedge would you assume that you could save by a good design? Well, you can see that little dotted line might give you a clue, but actually we don't know. We don't know because it's just a design on paper. How the house performs on the ground depends on another thing. It depends on build quality. And build quality depends on builders knowing and understanding what are the assumptions that the NatHERS system assumes as far as build quality and how to build to those assumptions. And unfortunately, builders was never taught any of this, so they don't know, typically, unless they have educated themselves. There's two spots where three things that builders need to look out for. They need to look out for doing the insulation right. You might have heard the old quote, if you've got 5% of holes in your insulation, the value of it drops by 50%. So it can have your insulation installation has a big effect on performance. That value is actually really just for ceiling insulation, but you get the idea. It does have a big impact. The other thing that has a big impact is how tight, what they call tight the house is. That's how well it limits unwanted air infiltration through the fabric of the house. Now, the NatHERS assumption is at what they call 10 air changes. You see that line in green. What you're looking at here is a graph of the CSIRO study back in 2015 where they got 20 new homes in the different capital cities and they measured how tight they were. And the way they measure how tight they are, they open up the door, they put what's called a blower door onto that front door, and it's basically a big fan that fits in a doorway, and that fan is connected to a computer, and the fan then turns on and sucks air out of the house, and they can measure from the resistance of the fan turning, they can measure how much holes is in the fabric of the house as to how hard it is for that fan to work, to do the job. And they crank it up to 50 pascals of pressure, which is the same as a 30 kilometre an hour breeze blowing over the house, or breeze I should call wind at 30 kilometres an hour. It's quite a high airflow, quite a high pressure. And NatHERS assumes somewhere around 10 air changes. I say somewhere because it does depend on what the thermal performance assessor inputs as far as their data as gaps and cracks and appliances and things that they put in the home. But somewhere around 10. Now, what they found, now this was back in 2015, but what they found was Adelaide and Hobart, on average, are under the assumption, so they're doing okay. But all the other cities are not. And Melbourne is at 19.7 as an average. Perth is at 25.5, so they've got a long way to sort of pick up. And Sydney is pretty high there too. Now, if I convert that to what does that mean to the actual star rating? Well, if that green line there is 7 stars, the new 7 stars, you can see that at 19.7 as an average, we're now at 5.8 stars from 7 stars. So lost 1.2 stars if the average back in 2015 is still the way we build. Now, I think we've actually come a bit of a way since 2015 on build quality. So I would expect that to come down a bit, but I still think we have a fair way to go to tighten up. So what do you do if you want to achieve an outcome on the ground as it should be on the paper? So you want to try and choose builders who can build for thermal performance. Now, these builders do exist. Obviously, ours know this, but I've got hundreds of builders now who follow Builders Declare, and I follow them back. And there's a lot of build companies now who are really starting to know about quality building, building tight, doing the insulation well. So if you are wanting to build a home, I would suggest that you check out the builders' website, socials, see if they're talking about performance construction. Are there any builders in the room, by the way? Few, excellent. It's actually really easy. You're probably all ahead of the game already, just coming to this. But it's pretty easy to upskill builders. And I was just talking to the councillor. This is one of the areas where I wish that the government would focus a bit of money on builders, because unless they know what to do, the scheme could fall over when it comes in, as far as the outcome that we're trying to achieve. But it's reasonably easy. A little bit of education goes a long way. And I would suggest for all new builders who haven't done it yet, get a blower door test organised, and that's a blower door, that thing that sits in there. Get your team there, get any trades who want to come along, use it as a team bonding day. It costs about $600, but it's not bad for a team bonding day. And what you do is when they turn the thing on, you can walk around the house and you can actually feel the surfaces and you can feel gaps and cracks. You can feel air coming in. The other thing, and that straight away starts to click for your trades as to where the gaps and cracks are and what they've got to do to make sure that that doesn't happen next time, what they have to cork, what they have to tape. The other thing that is a really powerful hint is to get for builders to get their project manager a thermal imaging camera and simply show it to the trades and show how you can take photos and you can see behind plaster, and let them know you might be doing a thermal blower door test later. And the trades straight away put two and two together. They understand, oh, this is a builder who not only is interested in the finish of things, but also wants it to perform well and can see under the plaster. They'll start putting insulation back in place. They'll start caulking as they need to, or taping any holes that they make. Okay. For designers and the average punter who doesn't know which builder to choose, this is also another thing that I'm suggesting for the industry. It is to, I've created here Design Matters and Builders Declare, something called the Thermal Performance Checklist. And this is this goes along with a talk, and if you are interested, you go to Design Matters, back catalogue, choose how to detail plan so the builder builds it to perform, and at the end of that you will get this. But that talk goes all over where standard construction fails to meet thermal performance. And the idea of the checklist, it's not extra things for the builder to do, it's just mental reminders of things to check off before the next stage starts. Because if you don't tape something, you don't cork it, you don't seal it before, say, the plaster goes on or the wrap is done or the cabinetry is placed, you just can't get to it later. So it's just a quality assurance checklist, and builders are very au fait with quality assurance checklists. For the builder, I think that this is more of a risk management thing. That's the way I see it. As we're moving to high performance and potentially promising net zero outcomes, we need a way for the builder to manage risk in case the house doesn't end up how the owner likes it and what the owner is expecting. You know, the first person they're going to point out is the builder and say, why is my house so cold? Right? And the builder needs a way to say, well, look, I've done all this checklists as we went along. I've taken my photos, done a blower door test at the end. Not necessarily on all projects do the blower door test, but have some evidence that you have undertaken the work satisfactorily. And of course, if you want to know more about that, you can go to Builders Declare, Facebook, Instagram, YouTube. And just letting you know, we've also got a new website coming out, which we've called Sustainable Builders Alliance. And on that website, another good place to find builders who sign the pledge to build better. They'll get their name up there. We don't warrant their work, but you know, if they're reading the stuff, they're probably on a better path than some others perhaps. Okay, so assuming you design well, assuming you get a builder who knows how to build to meet the NatHERS assumptions, if you design 7 stars, you should be able to save that much compared to the average home. If it's an 8-star design, you should get that much. 9 stars and 10 stars. And don't forget, in Victoria, our space conditioning wedge goes past halfway, so it's even bigger in Victoria or Ballarat, even more so perhaps. So something to look at here. You don't necessarily, or 2 things I want to say. You don't necessarily need to get to 10 stars to get net zero. To get a net zero outcome, you don't need 10 stars. 7 stars is just fine. The other thing to notice is how much of the pie is still left. right? The rest of the pie depends on what we choose as far as the plant that we put in there, the appliances that we put in there. And that's where the whole of home process, including those in the calculation, really is going to have the big impact. In fact, of the two, the increase to 7 stars or the inclusion of whole of home is much more important of the two. All right, so the last step here is with that wedge, we still haven't done quite as much as we can to limit the space conditioning energy use. We've still got this blue wedge, light blue wedge of heating and cooling to do. And the amount of energy that it uses depends on the appliance. Now, what I will be suggesting is that you choose reverse cycle air conditioning. Reverse cycle air conditioning is a type of heat pump, and heat pumps are one of the technologies that makes the whole net zero program or project doable and practical, achievable and cost effective. And just so up on the wall there, that's a reverse cycle air conditioner. You might know as a split system or a heat pump, all those words, heat shifter. In fact, the hydronic panel that you see there is also a heat pump hot water unit. What is a heat pump and why is it so good? So if I compare it against, say, gas ducted heating, which would be the standard for most project homes still, if I'm putting in gas ducted heating, the most efficient that gas ducted heating can ever be is 100% efficient. If 100% of the gas gets converted to heat in the furnace, 100% of that heat in the furnace gets through all the ducting without any losses into the house, that would be 100%. In reality, the best are about 93%, and probably most of what you get put into the market is around 80%, 80 to 85, or it starts at that level. Reverse cycle air conditioner, like the one you see up on the wall, starts at 300% efficient, and the best of them go up to 600% efficient, or almost 600% efficient. And I know that sounds crazy. It sounds like I'm some sort of crooked salesman here. The reason that that's the case is that they don't actually make heat like a furnace. They just shift it. That's the name, heat shifter. So it's worth just quickly looking at how they work to really get this locked in and understood. A reverse cycle air conditioner has an indoor head unit and it's got an outdoor motor, a compressor. And then it's got a tube going all the way around. It's a bit of a squiggly tube, but it's all one tube. Inside that tube is a refrigerant, and that refrigerant gets compressed and expanded. And the way it works, just say we're wanting to get some heat out of the thing. It goes out down the bottom run there, and it goes to, the refrigerant will go through something called an expansion valve. The expansion valve expands the refrigerant, which is a sort of a liquidy gas, and expand into its gas form. Now, when you expand a gas, it gets very cold. You would have maybe felt this if you've ever had a barbecue and you've tried to turn off or turn on the gas cylinder and a bit of the gas is shot out of the compressed thing that it's in and onto your hand. It feels cold. And once they expand the refrigerant, it goes down to about -40 or so. Now, it travels then past the fan, and the fan blows air across it. It blows the outdoor air across it. Now, the outdoor air might be 5 degrees outside on winter, might be 0 degrees, it might be a really cold winter night, might be -5. But compared to -40, it's really hot. And so it blows air across that really, really cold pipe, and the heat from the air goes into the refrigerant. The refrigerant then goes along until it gets to the compressor, that blue thing, yep, and that compresses it down. If you've ever squashed a gas, you'll know that it gets hot. And you would have felt this if you've ever pumped up a bicycle using one of those old hand pumps, where you're pumping up the bicycle wheel, and the hand at the bottom gets hot because you're squashing the air at that end. And so they squash the refrigerant back into sort of a liquidy form, and the heat comes out of it. And the heats in the indoor unit, there's a lot of very small copper pipes. They get very hot. The fan blows across those copper pipes, blows the heat into the room. When it does that, cools down the refrigerant a bit. The refrigerant goes around, it gets expanded, gets very cold, goes outside, soaks up more heat, brings inside, dumps it out. Goes outside, soaks up more heat, brings inside, dumps it out. So effectively, it's a sponge. It's a sponge. And it's transporting and shifting that heat. In cooling mode, it just works the other way. It then sucks up from the inside, dumps out outside. Sucks up from the inside, dumps out on the outside there. And it might only take 1 kilowatt hour of energy, say, to run this system, to run that circulation. But in doing that, it can transfer 3 kilowatt hours of heat, 4 kilowatt hours of heat, 5 kilowatt hours of heat. And this ratio of 1 unit of energy to getting 4 or 5 units of energy is called its coefficient of performance. That's the COP. So whenever you're looking to put, a unit up on the wall, just break out the specifications and turn to the page that talks about the COP. It'll be in a little table and you can see what number it is. The bigger the number, the better. I'd be recommending that you have a COP of at least 3. Now the EER, that stands for energy efficiency ratio. That's just when it's going in cooling mode, they give it another number, but it's pretty close to the same number. So there's our sevens, our wedge of blue in the space conditioning still remaining. So if you do use a heat pump, you can effectively make this much heating and cooling with less than that much energy, like about that much. Sorry, I went a bit out of sync there. So I can make that much heating and cooling with about 1/3 of the energy. Now that's the most that I can do with the space conditioning wedge. And that is the longest and most in-depth wedge. The other wedges, we can do stuff too, and it does not take as long to go through. All right, let's move on to the second step, which is water heating. Minimise hot water energy use. Now there's 2 things to minimise. That's the purple wedge there. 2 things to minimise the purple wedge. The first one is get water efficient appliances so you don't use as much hot water to begin with. And the other one is the hot water system that you choose. So 2 things. First one, 50% of your hot water goes through your shower in a standard home. So simply putting on a water efficient shower head is going to mean that you use less water. Make sure it's a good one. This is actually the quickest payback of anything you can do in the house. So, splurge on that nice shower head, get one that gives you a good shower. It will pay itself off very quickly. Also, for builders in the room, this is not part of the NatHERS whole of home. They don't actually consider shower heads. So if you do go a low flow shower head, effectively your house may perform a little bit better than the rating says it should. So it gives you a little bit of headroom in case you muck up a little bit elsewhere. Now the other thing here on the other side, you might recognise it looks very similar to a heat pump, doesn't it? Because it is heat pump hot water. Again, this one doesn't do the cooling, just does heating, and instead of blowing out heat into air, it just puts the heat into the water of the water tank. A good coefficient of performance for a hot water system is anything above 3. The best on the market are above 4. So for every 1 kilowatt hour of energy it uses, if it's 3, it puts 3 kilowatt hours of heat into the tank. If it's 4, it's 4 kilowatt hours of heat into the tank. So if we look at this, the purple wedge of hot water heating there, assuming that we put on maybe efficient shower head and some sort of efficient hot water. Now, solar hot water, by the way, is still a good way to get efficient hot water. With the solar hot water, 3/4 of your heat through the year comes from the sun with a good system. We typically don't put on solars anymore. We typically put on the heat pumps because we combine with photovoltaics. And one of the, not really an issue, but one of the ways to get a good payback on your photovoltaics is to do stuff with the energy when it's made. And if you're at work, say during the day, and you're not there to use the energy when you're making it, it's good to have a system that you can set to heat during the middle of the day. So there are some heat pump systems that we use that have timers that you can set them to heat when the sun is out. Typically, that's why we go that way. The other reason we go, most of our clients these days want to go all electric, and they want to do it from an environmental point of view. And the reason being, as I mentioned before, the carbon intensity of our electrical grid is going down as coal stations get retired and more renewables come online, and rooftop solar for that matter. It's making a big impact. As the grid greens, the impact of your house greens if you're on all electric. If you're on gas, you're still burning a fossil fuel. So gas can get a little bit greener, maybe if they mix in a bit of hydrogen, but not very much. So So just something to consider. I'm not necessarily against solar hot water, it's also a pretty good choice. But assuming that you do put on an efficient hot water system, you can make that much hot water with only a fraction of the power. Lighting, what can we do with lighting? Well, lighting's a really easy one. Lighting, you simply use LEDs and try and stay away from banks of downlights. Banks of downlights are not as efficient as luminaires, as lights that hang down into pendant lights that hang down into a space, because they light in more directions. Typically, one pendant light can replace a bank of four downlights. The other thing to consider with downlights, if we're thinking again about the tightness of our homes and how that affects our thermal performance, every time you cut a hole in the plaster, you're actually introducing a hole into what is part of the tightness membrane of the house. The plaster is probably tighter than the outside. Cladding is really hard to get tight. There's lots of gaps and cracks in cladding. So you get most of the tightness, you get a bit from the wrap when you put the wrap on, but you get a lot from the plaster as well in standard construction. So if you can minimise holes, you will have a tighter house. And so if you avoid lots of downlight, better to do so. If you can't, if you really must have downlights, just make sure there's something called IC4 rated. If they're IC4 rated, then you can run the insulation over the top. If they're not IC4 rated, they get too hot, and if you run insulation over the top, it will burn your house down. And the electrician is required by law to remove 50 millimetres of insulation from around that light fitting. But of course, the electrician never comes with a protractor and a tape measure. They'll simply just get their hand, they'll reach up through the hole they've just cut out in the plaster, they'll grab the insulation and they'll pull. And you can literally lose half a bat in that process. All right, so if you do use LEDs, you can get a little saving. It's only a little wedge, little saving on that little wedge. Cooking, again, is only a little wedge. But this is an area, in fact, where you can get a big saving for the client. And if you're a homeowner, you might consider this, because this is often the last holdout gas appliance in the house if you've gone heat pumps with your heating and cooling and hot water. If you get rid of this gas appliance, effectively you can get rid of the gas meter and you don't have to pay that connection fee anymore. That $1 a day connection fee, well, you can put that in your pocket instead, which is a nice thing over time for the life of the house. If you do, the one piece of technology that you can use here that will give you a bit of a saving is an induction cooktop, and that's the one that I would be suggesting. Most of our clients go induction cooktops these days and find them extremely responsive and easy to use, and on the same sort of price points as gas cooktops as well. And if you do go induction, they're a bit more efficient because with gas you lose a fair bit of your heat up around the sides of your pot as the gas goes around the sides. But induction's much more efficient at getting the heat into your pots and pans. So if you do put induction, you get a little bit of saving there. You can see how we're working our way around and we're minimising the energy needs in the house. All right, the very last one, appliances. Now, like I said, appliances, you don't get to interact. These are plug-in appliances. You don't get to interact with this as an assessor, but in reality, as a homeowner or as a builder or a designer, you can communicate with the owner who often buys the appliances because they do have a big impact on the running costs of the home. And if you're a designer or a builder, what you should be providing your clients, and this is what I like to do, is to show them these two things. One, another pie graph, like my pie graphs. This is a pie graph of plug-in appliance, average plug-in appliance use. And on the right-hand side of that pie graph, all those things down the right-hand side, those are all the white goods that typically go into a new build or a major renovation. Of those, of course, the fridge is the one to make sure you do right. And the big screen TVs also, you can use a lot of energy. But if you look over here on the right, I've gone to energyrating.gov.au. That is the site where they have databases of all the appliances that get the star ratings. Anytime you see a star rating on a plan, it's under something called GEMS, G-M-E-S, greenhouse something, something, something. When they rate them, they put them on a database, and you can search the databases if you want there to find out which appliances are are the most efficient. And if you do, you'll find that you can create a table like this to show clients what is the most efficient on the market, what is the least efficient on the market, and what would be the difference in running costs. And you can see that there's significant differences in running costs over a 10-year lifespan, which a lot of these appliances will last that long. So it does make sense to choose the highest stars, not necessarily the highest, and often once we give this information, clients won't always come back with the highest, but they'll often come back with 1 star down from the highest, and that's enough to get a significant saving. So if they do go shopping and come back with some reasonably high star appliances, you can get, again, a bit of a saving on that appliances tab. It's not more than that, because the appliances still use energy, and over the life of the house, a lot of things get plugged in: computers, consoles, phone chargers, all sorts of things. But you can see what we've done is we've eaten away at the pie here, and we haven't actually lost any function. We've got full functionality. All that we've lost is carbon dioxide being released to the atmosphere and the money that costs us to pay for that privilege of releasing carbon dioxide to the atmosphere. So you get the savings and not paying that energy, but you haven't lost any function. Your house is still as good as it always was, arguably better. All right, the last step on this little well-trodden dance is to offset with PV. And what we have found, just from our own practice applying this on with our own clients and our own builds, is that the average family in the average size home, 200 square metres or so, they will, if they've taken this route, they tend to break even from about 5 kilowatts of panel size and higher, 5 to 7 kilowatts, something like that, depending on the family. And when you consider that in the photovoltaic market, the average unit that gets sold these days is a 6.6 kilowatt system, you can see that this could actually be a model that can be rolled out broadly to the industry. So we can have significant widespread adoption of a net zero outcome. Of course, you don't have to use rules of thumb, and different climates will, necessitate different panel sizes and different outcomes. And that's where the software, which is Australia-wide, can do that job and do that rating and work out what you would need to do if you ask the assessor, what size panels do I need to break even for my appliance setup, for my rating in my house, in my climate, and the software will give them an answer. The only thing I would say about that is I would always put on 1 more kilowatts of panel if you're wanting to sort of guarantee a net zero outcome, because remember, these are predictions, and predictions, when they meet real world, often come a little bit unstuck. And assuming you put on some photovoltaics, you basically create as much power over the year as the house uses. Now, as far as your rating goes, when you do one of these ratings, if you put in very efficient appliances, you've got a 7-star home, you put in efficient appliances, for a lot of locations, that would be enough to get you over the line. But if you have 1 or 2 appliances that aren't so efficient, you might find that the rater requires that you put on a bit of PV. So here's the question here. What is the difference between a pass and net zero? The difference is, if you didn't have to have a solar system, to get to net zero, you'll end up with a small solar system. If you had to have a solar system, to get to net zero, you put on another couple of kilowatts of panel and you'll probably get a net zero outcome, unless you've got a really huge house, but for most homes. So the answer is the PV is a bit bigger, that's it. As an example here, this is a recent house, we've finished it now. One of our Carbon Zero series, or an iteration thereof. But just to show you, this was the Sustainability Pilot tool, not the Sustainability Victoria Pilot tool. They're actually updating this. I haven't seen the real one yet. But just putting it through the pilot tool, this house, it used energy from the grid, primarily at night time, and that created 4.38 tonnes of carbon dioxide over the year. But it had this had a 13 kilowatt system on the roof, a big one, because they wanted to charge their electric car as well. And that produced 17.4, or offset, if you like, offset 17.4 tonnes of carbon dioxide with the renewable power it sent to the grid for a net emissions of -13. That's instead of the average, which is +6. This was -13. So just to show that it can sort of work. That sort of brings me to the end. What are the savings here? Why are we doing this? So obviously for the homeowner, there's savings in the amount of money it's going to cost to run your home. And if you saw, I didn't say it at the start, but on that first pie graph, the average bill, at least when I put that slide together, the average dual fuel home bill, $2,200 or therefore thereabouts for if you combine your gas and your electric bill together. It's only gone up since then, and it's going to be going up quite sharply shortly when the changes come through from AEMO. So you'll be saving most, if not all of that. Oops. Obviously, if the house is detailed, the insulation is done well, it's nice and tight. If it's designed with some passive solar principles, it's probably got a nice connection to the rear yard and is well lit inside. So you might get arguably some extra comfort and sanctuary from it. For the environment is going to save that 6 tonnes of carbon dioxide a year from each home that we currently produce. And we're producing 200,000 new homes every year across Australia. So that's a significant saving just there. If you do go the next step, I don't have time to talk about that today, but if you do go the next step, there's a lot of embodied carbon in our structures as well. So that's the next thing to look at for the industry. And I would say for any builders or designers or homeowners who are building now, consider that even if you don't have an electric car now, within 10 years, you're probably going to have an electric car. There's also vehicle-to-grid technology or vehicle-to-house technology where the house is not only going to charge the car, but at night time, the car batteries are on average, around about 3 times the size of those house batteries that you see, the Tesla ones that get put on. So a lot more capacity is sitting there, and you can potentially run off your car as well. It also gives a lot of resilience if the power goes down. You can run the house on minimal circuits for a long time off a car battery. So it's worth setting up for that. And to set up for that is really easy. You just run a 32 amp cable that allows for the fastest car charging speeds. A 32 amp cable from the switchboard around to where you think a future charging point is going to be in the garage. Leave a couple of spare slots in the switchboard ready so that later the electrician can just connect it all up. Simple as that. So if you are thinking of designing, building, getting into a new home or major renovation, I invite you to walk the well-trodden path to a net zero home and make your footprints positive.